Okay. And so let's start, okay? So I'm glad to introduce Ling. Is that properly pronounced?
Yeah.
And she will talk today about evaluating strategy for tuberculosis to achieve the goal of WHO in China. And she will talk about a seasonal age structural model. So please, you can start.
Okay. Thank you. Thanks a lot to Pierre for inviting me. I remember we met in Miami for the first time.
Yes,
in
that's right.
US.
That's
probably
right.
2011. So more than 20 years ago. And
20 years ago already. Ooh.
Right, and also in Shanghai, 2018.
Okay, I visit you next time then.
Right. I was a postdoc working with Julian Reno, and you said you are his father's student. I still remember.
That's true.
Yeah, a small world.
Yeah. Oh, so we met a long time ago, in fact.
Right, yes. A decade ago.
Wow. Okay, so please.
So we are already old friends.
Yeah, sure.
Today I'm going to talk about tuberculosis, how to evaluate the mitigation strategies for this highly infectious disease in China. Probably TB is not, probably many people are not quite familiar with TB. Let me introduce this disease briefly. Tuberculosis, also called TB for short, it is caused by bacteria. Sorry. Usually, it affects the lungs of people very often. It is the world's top infectious killer, very fatal. TB is spread from person to person by air. So when some people are coughing, sneeze, they can release the germs into the air, so that when other people they take a breath, then they can take in the germs and become infected. Currently, multi-drug resistant TB remains a public health crisis and a health security threat. Let's see who are at a high risk of TB infection. TB mostly affects the adults in their most productive years. However, all people are at risk of TB infection. More than 90% of cases and deaths occur in developing countries. Usually, TB can co-infect with many other diseases, especially HIV. When people are infected with HIV, they are 80 times more likely to develop active TB. And the risk of active TB is greater in people suffering from other conditions, such as such other conditions that impair the immune system. So also people with undernutrition condition are 3 times more at risk. And worldwide, there were 1.9 million new TB cases attributable to the undernutrition. Also, the alcohol use disorder and tobacco smoking increase the risk of TB disease. And let's see what is the global impact of TB. TB is one of the top 10 causes of death and the leading cause from a single infectious agent. It is much higher than HIV. And this, as is shown in this figure, although from 2000 to 2020, the number of TB cases is decreasing, but the new and replace cases, number of new and replace cases are increasing from 2000 to 2019. And this is a map showing the countries that had at least 100,000 incident cases of TB in 2019. As is shown in this figure, India is the most affected country, accounting for 26% of the TB cases, followed by Indonesia, China, Philippines, Pakistan, and many other developing countries. So what is the current situation in China? TB is a serious public health problem in China. China is the third largest, has the third largest cases of TB. Also, the detection rate is low, and the multi-drug resistant TB is a major problem. Before, especially in the 1990s, the progress in TB control was quite slow. After the SARS epidemic occurred in China in 2003, the public health authority realized the weakness of the public health system, and the government increased its commitment and leadership to tackle the public health problems, increase the public health funding, revise the laws concerning the control of infectious diseases. Then the situation is improved a lot, but still not satisfying. This table is showing the goals of the World Health Organization. The vision is to have zero death, disease, and suffering due to TB, and the goal is to end the global TB epidemic. By 2030, ending the TB epidemic is among the health targets of the United Nations Sustainable Development Goals. As is shown in this table, the goal is to reduce the number of TB deaths by 90% by 2030 and 95% by 2035, and reduce the incidence rate by 80% in 2030 and 90% by 2035. And also this figure is showing the goal of the World Health Organization. With the current mitigation strategies, it is very difficult to achieve the goal. So we are proposing some possible strategies, such as the improved vaccination, so that it can prevent the infection in susceptible individuals more effectively, and prevent the reinfection in latent and recovered individuals. And another strategy might be improving the diagnosis so that the duration of infection can be shortened and the detection can be done much quicker. And also another possible strategy is improving the treatment strategy so that the treatment time can be shortened and the relapse rate of the recovered individuals is reduced. There are a lot of work has been done on modeling the transmission dynamics of TB since a long time ago. I have listed some of the references. In many work, they have developed like compartmental models, also continuous time, discrete time, all kinds of mathematical models to analyze the possible mitigation strategies, the transmission dynamics of TB. The models that I have listed here might not be sufficient. There are a lot of more references that probably were missing here. Most of these models, although some of these models have considered the age structure, and they also some models have evaluated the mitigation strategies. But to the best of our knowledge, most work have not taken into account the seasonality. And as shown by the prevalence data on TB, it shows obvious seasonal pattern. The reason for the seasonal pattern, although is not well known, but the higher infection rate in winter may be relevant to the increased periods that people spent in the very crowded, poorly ventilated housing conditions. And also the highly infectious viruses and lack of vitamin D lead to the immune efficiency, causing the TB to be reactivated in winter and spring. Also the diagnosis delay. Also it has some seasonal characteristics. So in the model, we not only take into account the age structure because people of different ages have different immunity of TB, and the transmission rates are quite different among different age groups. Also, we take into account the important factor, the climate factor into the model. So the transmission rate is modeled as a periodic transmission rate instead of constant rate that we have seen in most articles. The objective is to evaluate the effectiveness of the mitigation strategies, and to evaluate the possibility of achieving the goals of WHO in China. Next, I'm going to introduce the model. We assume that the newborns are vaccinated at the rate P1, but the leakness also exists, and some people, although they are vaccinated, but they can become susceptible, and also they might become exposed and infected after they contact the infected individuals due to the vaccine failure. susceptible people can be infected and go to the exposed class. The exposed individuals can become infected at this rate, mu1, sigma 1. Here we use this subscript 1 to represent people in the first age group from 0 to 4 years old. And we have another arrow here from E to I representing the fast progression due to the reinfection. Infected individuals can become recovered or can be treated. The treated individuals might die, and the recovered individuals, they might replace or they can be infected. So they go to E or go to I. And we also, for each age group, they can progress to other age group as they grow. So the rate is alpha. And we assume the natural death rate for each age group is B. So we have this D1 and DK. DK represent the other age groups. K is from 2 to 14. We have 14 age groups, but only the first age group will be vaccinated. This is the model based on the schematic diagram. We separated the age group 1 and K. So here K is from 2 to N. All the most terms in the model are very simple, just the linear terms. But the forces of reinfection is a little bit, it's non-linear, a little bit complicated. So let me introduce how the force of infection is formulated. The forces of infection among individuals, including susceptible, vaccinated, exposed, and recovered individuals in age group K, they are defined as this because people can be infected by infectious. So infectious individuals and treated individuals. Although people are treated, but they might still carry the virus, carry the bacteria. Here, this CKJ represents the average number of contacts between between people in age group K and age group J. Beta K is the probability of infection when they contact infectious people, and the omega J represents the coefficient that reduces the transmission rate due to the treatment in age group J. When people are being treated, they might have smaller probability of transmitting the disease to others. So that's why we are using omega J here. As it's seen, the model is quite complicated. And next, we are trying to simplify the model. We assume the population reach an equilibrium age distribution with exponential growth in this form. Here, N is the total population in age group K, and PK is the initial size of the population of K's group, age group. U represents the constant growth rate, and then PK is satisfying this function, and the birth function can be expressed as this equation below. The birth population per unit time can be written as this. here the P1 is equal to the initial population for the first age group. And then we use these fractions to represent the people in each as a fraction of people in each compartment for each age group. Then the model is a little simplified as this, although a still huge system. As we know, the basic reproduction number is a commonly used threshold in mathematical epidemiology. It can be used to evaluate the transmission potential of a disease. So first, we calculate the basic reproduction number. Since this is a non-autonomous system, it's a little bit complicated to derive the basic reproduction number than other models. We referred to the approach in this reference. At the bottom, define a linear operator. Here, this capital L is called the next generation infection operator, and the spectral radius of L is defined as the basic reproduction number denoted by R0. R0 is the spectral radius of this operator. And we introduce this linear T-periodic system to derive R0. Referring to the theorem in the references, these statements hold. So if the spectral radius is greater than 1, R0 is greater than 1 if and only if the spectral radius is greater than 1, and less than 1 if and only if the spectral radius is less than 1. So the R0 depends on the spectral radius of this operator. The basic reproduction number can be used to evaluate whether the disease can exist or persist. So disease-free periodic solution is globally asymptotic stable if R0 is less than 1, and unstable if R0 is greater than 1. And for the uniform persistence of the disease, also depending on the basic reproduction number, if R0 is greater than 1, then the system has at least one positive periodic solution. However, we notice that even if R0 is less than 1, the epidemic still may take off, as is shown in this graph. Here, in this part, R0 is less than 1, but the system has at least one stable positive periodic solution and a stable disease-free periodic solution. And this part, the green part, represents a stable positive periodic solution. And the red part is the unstable disease-free periodic solution. The dark blue part is the stable disease-free periodic solution. This light blue part is the stable positive periodic solution, although R0 is less than 1. I already mentioned. So even if R naught is less than 1, the epidemic may not die out. We used the publicly available data collected to analyze the relationship between the prevalence and the age. The figure on the left is showing the prevalence in different age groups. Here we have 14 age groups. The interval is 5 years. And the figure on the right is showing the age versus the proportion of the population. And these data are all for China. Here, the prevalence represents the prevalence represents the cases per 100,000 individuals. And from the data on the previous page, we analyze the data and calculate the standard deviation and the 25% percentile and the 75 percentile of the data. For the monthly, we use the monthly prevalence data. And also we did the correlation analysis here. The x-axis represents the age group, and the y-axis represents the TB prevalence. These data are showing that the prevalence of TB was highly positively correlated with the age of individuals infected with TB from 2005 to 2017. So the age structure is really important. So that we use the age to identify the heterogeneity among the different groups of people. As I introduced the first of infection, there is coefficient called the contact rate, CIJ. So we calculate the contact matrices to find the parameter CIJ for the force of so that we can calculate the force of infection. The figure on the left represents the daily average number of contacts. And because we are using the monthly data, so we translate it into the figure on the right, representing the monthly average number of contacts per person in each of the age group. Because we take into consider the seasonality, the transmission rate is varying with time, it's periodic, and we need to parameterize beta K. So we use the wavelet spectrum analysis. Here we have these figures A and B. Figure A represents the wave spectral analysis of monthly new TB cases. Here's a different color representing the red represents high power values, and followed by orange, yellow, blue. And the figures B represent the average wavelength spectrum. The blue line represents the average wavelength spectrum, and the red dashed line represents 95 confidence contour.
Excuse me.
Okay.
You need to
Go ahead.
You need to conclude now. It's 30-minute talk.
Oh, sorry.
Right.
I forgot. I thought it's an hour. I'm sorry. Okay.
Okay, please.
Okay. I think I'm almost done.
You can make a transition, okay? I give you, say, 1 more minute, okay? Okay.
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 So the following part are all about how to find the beta k, and then these are the curve fittings, and how good is the curve fitting and the basic reputation number. Then we did some sensitivity analysis, and then we tested the different mitigation strategies, the vaccination, diagnosis, and treatment, and also the combination of multiple intervention strategies. And here is the end. So in the model, we take into account the age structure and the seasonal transmission rate. We find that the basic reproduction number is always greater than 1, so that the TB is uniformly persistent. And we found the positive periodic solution. The different mitigation strategies showing that the goals of the WHO in 2050 cannot be achieved because of the reinfection in latent and recovered populations if the current strategies do not change. That is the main conclusion for this work. And there are still some limitations, such as we didn't take into account the behavior change, which is very important, and we will leave it for future work. And this is our research group in China. By the way, we still have some job openings. If you are interested, feel free to contact me. The middle line are the PhD students in our research group working on different mathematical biology topics. And welcome you all to visit us in Harbin. Thank you. Sorry for taking so long.
That's fine. Thank you very much for this very interesting presentation. Are there questions? I will have questions anyway, so.
Okay, go ahead.
So no, I would like to see, so it's a very challenging problem you are considering to try to describe the seasonality. And so I would like to see how good is your fit to the data. And I didn't, you chose a transmission rate that is time dependent. And I would like to see if yeah, probably that is a curve fitting for different.
Right, yes.
So you can
solid line is the number, the activated cases. The red line.
Right. You can reproduce the data very well. What are you plotting now? The total number of cases or what? Is it?
Yeah, from 2005 to 2017.
Right.
Yeah.
And you are using
for different age groups, the prevalence. Yeah, prevalence data. And here is for different age groups,
Of course, it
we did
becomes
the
less good,
fitting,
right?
yeah, right. Also, the red line is the cases, number of cases.
Your fit for the prevalence is pretty good already.
And
Well,
also here, this figure is the dots are
the data, right?
right. Yes.
Yeah. So you can follow. Actually, you can follow the age distribution very well, in fact.
Yes, I think so. Yeah.
So show again your fit to the data. The first one you show, I want to see. So no, stop this one. So this one you get on the x-axis is what? No, the previous one. The one with the prevalence. Yeah, this one. What is the x-axis here?
I see.
X, the horizontal axis.
And the x-axis is we have 14 age groups.
That's the age group.
Right.
Oh, I see. So it's not a time. I thought this was a time. You try to fit the time. So you are not fitting the time distribution. Huh? You are fitting the number that is with time.
Right. This one is with time. And see, the x-axis is months. The months.
Yeah. So you see the season here. Oh. So you get the data month by month?
Right, yes.
Oh, I see. Okay, yeah. So it's very, very challenging, right? Maybe, I was thinking that maybe there is a need for some, apparently there is a need for some sort of phenomenological description of the data, in fact. Try to give a sort of model for the data, without the epidemic, in order to reconstruct the transmission rate, in fact. Actually, we did a lot of things like that with Quentin, by the way, Quentin Gayet, who is here, and other people. But it seems to be very interesting to consider the case with time-dependent, not time-dependent, but what I mean, seasonal. The problem of seasonal infection is still not considered. We did not consider that at all, in fact. But that would be really interesting, I think. Really interesting to consider this. But it seems to be very challenging. You consider a very complex problem with a lot of compartments, right? And
right.
actually,
really large too. Yeah.
Very difficult, I think. Maybe you need to merge together some compartment, like, for example, the child, to get more.
Right. Yeah, that is a great idea. Yeah.
That would be maybe more helpful. And but I think the point is, maybe since you don't know a priori the change from one year to the next, right?
Right.
So my question was at the beginning: is the same model always working well, in your opinion, from year to year? You just change some parameter value and it works relatively well. Can you show the transmission rate again, the time-dependent transmission rate?
Okay. Right, here.
This one, yeah.
Right.
So basically you just have 3 parameters here, right? For each age group, right?
Yes.
And
yes.
you are, from year to year, you use the same, right? You fix the parameter once for all, just for each age group, right?
Right.
The parameters are not time dependent, right?
Right.
I see. Okay, I see. So this is very challenging, in fact, probably it might be time dependent. Huh? Might be time dependent, but maybe, yeah. So no, that's a very interesting question, in fact.
Thank you.
No, but it's very challenging indeed. It's very challenging. But maybe the other way around would be even more. Since you get the data, you could go the other way around, try to understand what should be beta. You see? From the data, try to evaluate beta. You see?
Actually, the beta is derived from the data. Right. Actually, this model is not used for prediction. We use the data to evaluate to find the parameters and to evaluate the mitigation strategies.
No, I understand that, but what I mean,
So
is that
here, like we use the data to derive beta.
Okay. Let's see.
Yeah, we use the cumulative number of cases.
Okay. Cumulative number. But how to connect that with the transmission rate and so on? It's not easy, right? Yeah. I mean, with how to connect. You use the best fit to the data, do you?
Right. Yes.
Yeah.
We use the MCMC to. We use the Monte Carlo Markov chain.
Oh, okay.
Yeah.
Okay.
To estimate the unknown parameters.
Right. Okay. Maybe I'll let the other people. Are there any other questions to this very challenging presentation? In fact, I think it's a very challenging problem, and very interesting. In fact. Okay. So
can I ask a question?
Very good. Please go.
Yeah, thank you very much for your talk.
Thank you.
Yeah, I want to ask whether you could also like consider some other parameters in the model as to look at the seasonality, because I don't know from your country what actually drives the seasonality. So, like, what are the drivers of that seasonality? Is it rainfall? Is it population movement and all that? So I really want to know.
But I think maybe the rainfall, the population movement affects, causes the seasonal pattern in the prevalence data. I think mostly it is reflected in the transmission rate. The transmission rate will have the seasonal pattern. Like in spring and winter, probably the condition, the ventilation condition is not good, and it is more easy for it. There is a higher probability of transmission from one person to another.
Okay. Yeah. So
probably there are some reasons, but to formulate the model, so we reflect this into this using this transmission rate, and maybe it is related to the like rainfall, temperature, or other factors.
Yeah. basically you want to.
Yeah, like usually the temperature and the rainfall they have, they are also modeled using such functions.
Okay. Can I see your your basic reproduction number?
Okay. Let me go back. Because this model is very large, it's difficult to have the explicit expression for or not. So
Okay,
yeah,
I've been able to,
so
because
the spectral radius of the operator.
okay.
Yeah.
Okay, so it has some dependent on the periodicity, right?
Right.
Okay. So, but I think it will also be a good idea if you can incorporate like either the rainfall data or the temperature data to show the true drivers of the seasonality, to prove it.
Right. Yeah, that is a great idea. Thanks a lot. Yes.
Yeah. So maybe I will also try
it-
to, maybe can you send your email address? I would like to contact you.
Okay, sounds great. At the first page here.
We'll put the slide on the web page of the webinar.
Yeah,
Okay?
LXUE.
Okay, thank you.
My, yes, the abbreviation of my first name and the last name at hrbeu.edu.cn.
By the way, a last.
Yeah, I'm looking forward to more discussion with you.
Okay, good. Thank you very much.
Yeah, and thanks a lot for the great suggestion. It's very helpful. Yeah, I think using more data, it would be more accurate.
Yeah.
I would like to ask you a last question before stopping. And at some point you mentioned that the R0 was less than 1, but the epidemic was emerging.
Still take off.
So I didn't get that. Why is that, in fact? Why?
For many models, if R0 is less than 1, the epidemic will die out, right?
Right. Normally, this is the idea.
Yeah, but for some models, probably, like this one.
What do you mean? What do you mean will go out? Means this is due to the nonlinear term, or this is due
for
to
some models? If R0 is less than 1, then the infected individuals will become, the number of infected will become less and less, and finally go to 0. But for this case, like this one, for this one, yeah, although R0 is less than 1, we not only have this disease-free, we also have this positive periodic solution.
Oh, really? Yeah. So, that's really, so it means that you get
like some bifurcation, like in some models, although R0 is less than 1, the backward bifurcation occurs.
Right. Backward bifurcation.
Other like endemic equilibrium
so
also exist simultaneously.
So that's due to the nonlinear structure of the model, in fact. Not due to the linear, but to the nonlinear. So you
right, yeah.
You get some,
probably also is caused by the seasonality, I guess.
Okay. So you can observe that in this model, in this.
Right. Yes.
That's due to the vaccination, probably compartment and so on.
Also the vaccination, right? Vaccination.
Yeah, I see. Okay, thank you very much. Very interesting. Very interesting. Thank you. So I will we will stop here, and I think the next talk will be next month. Okay, so we continue next month this webinar, and I will indeed put the movie of your presentation and your slide on the web page today, in fact. Okay. So
Thank
thank you
you.
very much, everybody, for coming. Okay. Okay. So bye-bye.
Thank you, Ling. Thank you.
We
Thank
can
you,
talk a little
Father.
bit. We can talk a little bit more. Okay. I will stop to record now. Let's see.
Okay.
Arrête.